In Module 4.2, we will look at how to store electricity to balance variability through time. We can look at this conceptually again with time series. Instead of trying to move the generation and demand time series closer together, we chop pieces of the generation time series off when it is above demand and move those cut off pieces to times when the generation time series is below demand. We do that by storing unused generation for later use. You might recall that I said in the third week that electricity cannot be stored, and that's still true. Electricity can only be stored indirectly, for example, by powering a chemical reaction inside a battery, which can later be reversed to generate electricity again. But in practice, we can still say electricity storage. There's actually a wide range of different technologies with which we can store electricity by transforming it into something else and then back. I've indicated the most important ones here and sorted them by the time duration of storage for which they are useful. Something like a capacitor might store less than a second of electricity demand to deal with very, very short-term fluctuations. While using hydrogen, as we'll see later, we might store months and months worth of electricity. We could easily spend an entire course talking about just these different storage technologies, and you can read up on these options on your own later. For now, I'll just indicate which ones are already used at a large scale. Batteries, especially lithium-ion batteries, which is exactly the same kind of battery also used in electronic devices like your phone or in electric cars. Pumped hydro, which we already mentioned, which stores electricity in the form of water. And heat storage. We mentioned concentrating solar power plants with heat storage earlier. Note that the two options at the very right, heat and hydrogen, I've indicated as options with non-electric uses, because in addition to turning them into electricity, you can also use heat and hydrogen for their own separate purposes, like heating or industrial processes, or for hydrogen also as a fuel. So this makes these electricity storage options more flexible, as we will also see in the next module. For now, let's look closer at two particularly important options, batteries and hydrogen. First, batteries. Just like photovoltaics, their strength is almost infinite scalability. The same battery technology that powers your tiny smartphone can be scaled up to, say, 2,500 times larger system that runs in combination with some rooftop PV panels to balance the shorter-term variability of the PV system. Or scaled up by a factor of millions for a large grid-connected battery, like this one here in Australia, that can easily provide backup electricity for a few hours for a small town. Now, hydrogen. Let's look at an example, a simple home with a rooftop PV system. The home is connected to the power grid, so it can get electricity both from the PV panels on the roof and from the grid. Now, we looked at batteries earlier. A typical lithium-ion battery has a round-trip efficiency of about 95%. So if we store electricity and retrieve it later, we lose about 5% of that electricity along the way. That's not too bad. Now let's look at hydrogen. You can see this a bit more involved. An electrolyzer uses electricity to split water into hydrogen gas and oxygen gas. The hydrogen we can store in various ways, for example in a tank. It requires a compressor and pumps and various equipment, all of which needs to be designed to deal with hydrogen as it is a rather volatile gas. Finally, we can later direct the hydrogen out of the storage tank into a fuel cell, which generates electricity, as well as water as a harmless byproduct. It's basically the reverse of the earlier process of the electrolyzer. Now, given the various steps involved, it's not surprising that the round-trip efficiency is a lot lower. Typically, only around 45% of the electricity put in at the start comes back out in the end. So you might wonder, why would this ever make sense compared to a battery? The reason is a combination of two facts to do with the generation and the hydrogen part of our system diagram. First, recall that both wind and solar power, but especially solar power, have a strong seasonal variation, seen here again for Germany in 2019. And also recall that at the start of this week, I said that for the hardest problem with renewable variability, the scale of months to entire seasons, there's still quite some uncertainty about how it will ultimately be best resolved. But here, using hydrogen for storage might actually have a strength. It is split across several separate components, meaning it's easy to dimension these components individually. We can use relatively small electrolyzers and small fuel cells, but a very large storage system, something like this large gas tank here. Then slowly but continuously produce hydrogen through summer, and then slowly but continuously turn it back into electricity in winter. Building large storage tanks is relatively cheap, much cheaper than large batteries. So the low 45% efficiency is still there, but for seasonal balancing, the cost might be worth it. This is important because as we've seen, geographical balancing alone cannot fully solve the seasonality problem. And by the way, we are also highlighting an important general point here. In a system built around variable renewable generation, there will often be periods of overproduction of electricity. Why? Because it makes sense, for example, to build enough PV capacity to generate sufficient electricity through most of spring, summer, and autumn. Which implies that on a very sunny summer days, or even on sunny days in other times of the year, that capacity will supply much more electricity than actually needed. Turning that overproduction of electricity into hydrogen might make sense, even with the high losses along the way. And indeed, it seems credible that batteries might play a key role in balancing shorter-term variability, hours to maybe a single day or so, while hydrogen for storage might play a key role in dealing with longer duration variability. It's a little bit less clear what storage technology will be best for the intermediate period, a few days to a week or two. That could be batteries and/or hydrogen, or something else like pumped hydro storage or compressed air storage. Okay, so we've dealt with grids and we've dealt with storage. And in the next module, the final option we will look at is flexibility.